Hello everyone, this side Manisha Mishra, Assistant Professor in Mathematics, Applied Science Department at St. Andrews Institute of Technology and Management, Gurgaon. This college is affiliated to MATHS-3 University, Rohtak. Today our topic will be Alembert solution for wave equation. So I have already told you about wave equation in our previous session, and I will share two example related to wave equation. Then by using initial conditions and also boundary conditions. Right. In previous session, I did not use a boundary and initial condition, but today I will share two examples of wave equation by using the boundary and initial conditions, right? So D'Alembert solution for wave equation is very important. It will ask at 15 marks question in your final semester exam, and I'm damn sure about it will 99% can come in your final semester exam, right? So prepare D'Alembert solution for the wave equation, right? Now I'm going to share one example related to wave equation, right? So solve the wave equation del 2u upon del t square is equal to a square del 2u upon del x square, right? So this is your second order partial differential equation. Now, under the condition u is equal to 0 when x is equal to 0 and x is equal to pi, means at x is equal to 0 and x is equal to pi, the solution is 0, right? And derivative with respect to t at t also we are getting 0 when t is equal to 0. When our time is 0, then our solution is also 0, and u at time is equal to 0 is equal to x. 0 is less than x less than pi. Now whatever boundary and initial conditions are given, doesn't matter, you have to remember your procedure, right? Condition is here x is equal to 0 or not, x is equal to not equal to 0, whatever is given, but you just follow your procedure, right? So now we can see that the solution is of the form. So we have already we have already our solution of the wave equation like this solution I told you in our previous session, right? This is your wave equation, and we solved this wave equation by applying three cases. K is a negative integer, K is a positive integer, and K is equal to 0. So which one will be your periodic function solution? That solution we considered, right? So you can see that this is your final solution, means when k is a negative integer. So we got this solution in our previous session. Now we will use this solution because we know that the solution of the wave equation, so no need to find again, apply the case 1, case 2, case 3, and case minus in positive square will be considered. So then no need to drive here, right? So we know that the solution of the wave equation is this one: c1 cos px plus c2 sin px, c3 cos pat plus c4 sin pat, right? So here in place of c there is given a square, right? So our c will be replaced by a. Now we know that our above solution apply boundary and initial condition in our first equation. So first condition is when x is equal to 0, your solution is also 0. So just apply here, when x is equal to 0, your solution is 0. So 0 is equal to this into this one. I told you that this solution can never be 0 because this is a part of the solution. If if this bracket will be 0, that means our whole solution will be 0 and hypothesis will be failure, right? So C1 constant must be 0 here, right? Now your c1 is equal to 0, then your equation 1, that means this equation first will be uxt is equal to c2 sin px into c3 cos pat plus c4 sin pat. This is your equation second. Now there is another condition here: when x is equal to pi, your solution is also 0. So just write x is equal to pi here. So u pi t is equal to 0. So 0 is equal to C2 sine p pi into C3 cos this one. Right? Now again your C2 does not equal to 0, because if C2 is equal to 0, that means this solution second will be 0 here. That means whole solution will be 0. So this is not possible. Your this bracket also does not equal to 0, because whole solution will be 0. So your sine p pi must have is equal to 0, must have be 0. So sine p pi is equal to 0. So sine p pi is equal to sine n pi. P pi is equal to n pi. So we can say, see that our p is equal to n here. Right? So we are getting the value of p. Now put the value of p in equation second. So your equation second will be u xt is equal to c2 sine nx c3 cos ant plus c4 sine ant. Your second solution will be like this. Now just u xt is equal to sine nx, c2 is multiplying inside the bracket, so we are getting this one. Now constant C2, C3 and C3, C4 as replacing by B1 and B2. We can write constant any thing, right? Just mention your theory that what you are doing here. So uxt is equal to sine nx b1 cos ant plus b2 sine ant. This is your equation third. Now second condition is given, del u upon del t is equal to 0 when t is equal to 0, and ux0 is equal to x is also given. So del u by del t is equal to 0. So we need to calculate del u by del t from here. So del u upon del t is equal to n sine nx, because b1 cos a and t differentiation will be minus a and b1 sine a and t. So n is outside. b2 sine cos a and t into n is outside here, right? Now del u by del t is equal to 0 is given when t is equal to 0. So just apply the condition here. So 0 is equal to n sine nx minus a b1 sine 0 plus a2 cos 0. That means 0 is equal to n sine nx a into b2 here. Right? Now 0 is equal to sine nx a b2 n. Now here if sine nx is equal to 0, that means your whole solution will be 0. This solution will be 0. Right? A b2. So if your a n is equal to a will be 0, then that means you here a will be 0, a will be 0. So your solution is not clear, right? So a constant b2 must be is equal to 0 here. Now from the equation third, put b2 is equal to 0 here. So we are getting uxt is equal to sine nx b1 cos a n t. Right? Now we can write it, because n is an integer, so it will be uxt is equal to bn sine nx cos a n t. Right? We can write this one, because it is for n variables. So uxt is equal to summation n is equal to 1 to infinity b n sine nx cos a n t. Now another condition is given, ux0 is equal to ux0 is equal to x, 0 is less than x less than pi. So just apply here ux0 is equal to x. So ux0 means here t is equal to 0. So x is equal to summation n is equal to infinity bn sine nx into cos 0. So we are getting x is equal to summation n is equal to 1 to infinity bn sine nx, and your bn is equal to, this is your Fourier expansion. So your bn is equal to 2 upon pi 0 to pi x sine nx into dx. 2 upon pi is in your Fourier's formula. 0 to L, so L is given pi here, that means length of the string, and x sine nx. So x is your function and fx is your sine nx. So x into sine nx dx, just different, integrate with respect to x, and it will integrate by partially. So first as a first function as it is integration of second, so sine nx integration is minus cos nx upon n, minus differentiation of one is x, integration of sine and integration of sine nx is cos nx, and again integration. So again integration, so cos nx integration, again you will get minus sine nx upon n square. After applying limit, so limit rule is upper limit minus lower limit. So x upper limit, so minus pi upon n cos n pi minus 0, this will lower limit, so 0 into this one, so whole will be 0, minus minus plus and again minus minus sin n pi upon n square plus sin 0. So we know that sin n pi is equal to 0, sin 0 is equal to 0, so we are getting minus pi upon n cos n pi, and our cos n pi value is always minus 1 to the power n. So just put bn value in our solution. So hence the required solution is u xt is equal to minus 2 summation n is equal to 1 to infinity minus 1 to the power n upon n sin nx into cos a n t. So this is your final answer, right? Now always in exam these types of question will be asked, right? There will be no change in method, means you know the solution of the wave equation. When it said that find derive the solution for the wave equation or something like that, then you will apply the cases here, right? Otherwise use the direct solution for the wave equation. Now solution of wave equation by D'Alembert's method. So what is the solution of wave equation by D'Alembert's method? So we know that one method, as we have already seen in previous session and also here in this session. Now by the method of D'Alembert's. So we know that our wave equation del 2y upon del t square is equal to c square del 2y upon del x2. Previous method is our separation of variables and this method is D'Alembert's wave method. So initial condition, we know that y at x0 is equal to fx and del y upon del t is equal to 0 when t is equal to 0. So let us introduce the two new independent variables, u is equal to x plus ct and v is equal to x minus ct. So for the solution of wave equation by D'Alembert method, we will choose two variables u and v here. Right, we are considering two independent variables u and v, and we will get our solution by using these two variables, right? So u is equal to x plus ct and v is equal to x minus ct here, so that y becomes a function of u and v. So del y upon del x we need to calculate here, del y upon del x, del 2y upon del x2 and del 2y upon del t square, right? So for the calculation of del 2y upon del x2, we need first order derivative. So del y upon del x, we can write del y upon del u into del u upon del x, right? Plus del y upon del v into del v upon del x. If y is a function of u and v, then you're differentiating del y upon different partial derivative del y upon del x. We will write it by the chain rule. This is called chain rule. That means if y depends on u and v, then del y upon del u into del u by del x plus del y upon del v into del v upon del x. This is the equation second. Now u is equal to x plus ct. This one is your first equation. So u is equal to x plus ct. So we need to calculate del u by del x from here. So it will be 1. Del u upon del t, it will be c. Del v upon del x 1. Del v upon del t is equal to minus c. Right? So just write all these values in second. So del y upon del x is equal to del y upon del u into 1 plus del y upon del v into 1 here. Right? So we are getting del y del x is equal to del y upon del u plus del y upon del v. Now we can write this equation as del upon del x is equal to del upon del u plus del upon del v. Right? Now second derivative, so del 2y upon del x2. So for the calculation of this one, we can write this equation as del upon del x into del y upon del x, right? We know that del upon del x value, so del x upon del x value is del upon del u plus del upon del v into del y upon del x value is this one, del y upon del u plus del y upon del v. So just operate this. So you will get del upon del u and this bracket plus del upon del v, this bracket. right? Now del 2 y upon del u2 plus del 2 y upon del u del v, del 2 y upon del v del u, and del 2 y upon del v2, right? We can write this as this one, and this one are equal, so it will be del 2 y upon del x2 is equal to 2 times of del 2 v upon del u del v, right? Now, next target is find del y upon del t. So del y upon del t, again by chain rule, you can write it del y upon del u into del u by del t, and del y upon del v into del v upon del t, right? Now, we have already know the value of del u upon del t. You solve this here. Del u upon del t is c, and del v upon del t is minus c. So just write here all the value. So del u upon del t c, and del v upon del t is also minus c. So after solving this, you are getting del y upon del t is equal to c and this value, right? Now, you can write it del upon del t is equal to c and this bracket. Again, second derivative with respect to t. So del 2 y upon del t square, you can write it del upon del t and del y upon del t. So we know that del upon del t value is this one and del y upon del t value is this one. So just write all these value and same method. So just multiply inside the bracket and you are getting del 2 y upon del t square is equal to c square, and this value, I again this will be both are will be equal, so it will be 2 times of this one. Now we have all the values what we need for first equation. So just write all these value in our first equation. So c square del 2 u, that means del 2 y upon del t2 square value is this one. So just write here, and left hand side c square del 2 y upon del x2 value here. This is your del 2 y upon del x2 value, right? So c square cancelled out, and all derivative will be cancelled out except this these two, right? So these two will be remaining. So just write it here, and it will be 4 times is equal to 0. That means del 2 y upon del u del v is equal to 0, right? So watch carefully, because now the process is starting from here. So del 2 y upon del u del v is equal to 0. So first integrating with respect to v. So after integrating, you can see that del y upon del u will be remaining, and fu is your integrating constant with respect to v, right? We are doing integrating first with respect to v, so our integrating constant will be fu here, right? Just opposite to integrating variable. So v is the integrating variable, so fu will be constant here. Now again integrating with respect to u, so y will is equal to integration fu du plus iv. That means integration is going with respect to u, so our integrating constant will be psi v here with respect to v, right? Psi v is a constant in respect of u, right? So we have y is equal to fu du plus psi v. So you can write fu du as phi u plus psi v, where phi u is equal to integration fu du. These are the constants, so we can replace by other constant, right? Now y xt is equal to phi u plus psi v. Now we know that the value of u and v, so just write u is equal to x plus ct and v is equal to x minus ct here. This is your equation 4, and this is the Alembert solution of wave equation, right? Now after this, we will apply our boundary conditions and initial conditions. So apply initial condition. So initial condition is given yx0 is equal to fx and del y upon del t is equal to 0 when t is equal to 0. So differentiating 4 with respect to t, because we need del y upon del t. So del y upon del t is equal to phi dash x plus ct into c minus psi dash x minus c2 into c. So del y upon del t, c is a common, then right outside. This is our equation 5th. Now apply condition del y upon del t is equal to 0 when t is equal to 0. So 0 is equal to c phi dash x minus c psi dash x, and 0 is equal to, we can write it phi dash x is equal to psi dash x, right? Now integrating again, so we can see that phi x is equal to psi x plus b is also integrating constant. Now again substituting y is equal to fx and t is equal to 0 in equation 4, because this is our second condition, right? Y at x is equal to 0, sorry, y at x and t is equal to 0 is equal to fx. So our equation 4 is this one, so just apply here. So we are getting fx is equal to phi x plus psi x, right? After applying in equation 4, we can see that fx is equal to phi x plus psi x, right? Now we are getting phi x is equal to psi x plus b here, so just put this value here, right? So from equation 6, fx is equal to psi x plus b plus psi x, so fx is equal to 2 psi x plus b. So we need to calculate psi x from here. So psi x is equal to fx minus b upon 2 here, right? Now, if we are getting psi x, that means we can calculate phi x from here, right? So phi x will be fx plus b upon 2, right? Now, putting the values of phi and psi in equation 4, right? So this is your equation 4, this one. So just write all these values here. So phi x, so we are getting phi x is equal to fx plus b upon 2. So 1 by 2 is outside fx. So in equation 4, just try, just watch carefully. Here phi x, so x is replacing by x plus ct. So your phi x solution will be fx plus ct plus b plus half psi x plus ct. So psi x is your fx plus ct minus b upon 2. That means x is replacing by x plus ct. Here x is replacing by x minus ct. Just solve this and you will get your final answer of D. Alembert solution is y of xt is equal to half f of x plus ct plus f of x minus ct, right? X is replacing by x plus ct, and in second psi x is replacing by x minus ct. So just replace x by x plus ct and x by x minus ct, right? So this is your final solution of wave equation. There is another example here. The vibration of an elastic string is governed by the partial differential equation. This one, this is your wave equation. The length of the string is pi. That means at x is equal to pi is given and the ends are fixed. The initial velocity is 0. That means u is equal to, velocity means del u by del t is equal to 0, and the initial deflection is ux. 0 is equal to this one already given. Find the deflection uxt of the vibrating string. That means here there are conditions given that velocity del u by del t is equal to 0 at t is equal to 0, and ux0 is already given at t is equal to 0. Here x is equal to 0 and x is equal to pi is given, and the ends are fixed, so u is equal to 0 is also here, right? Now u is equal to c1. We know that the solution of this equation, so compare with this, so c is equal to 1 here. We know that the solution of the wave equation, so just write the solution here. Now we know that putting x is equal to 0 and u is equal to 0, initial condition, so just c1 is equal to 0, same as it is. After putting x is equal to pi and u is equal to 0, so your p is equal to n, we are getting, on substituting the values of p into, so u is equal to, we are getting this equation, right? Now third initial condition is del u by del t is equal to 0 when t is equal to 0. So calculate del u by del t from here. So you can see that C4 is equal to 0, because this can never be 0, because whole solution will be 0. Now uxt is equal to C3 cos nt into C2 sin nx. We are getting this solution. So uxt you can write C2 C3 cos nt into sin nx. This is your equation 4. Given condition is u at x0 is equal to 2 sin x plus sin 3x. So just apply here, put t is equal to 0 in equation 4. So 2 sin x plus 2 sin 3x is equal to C2 C3 cos 0 sin nx. Then final we are getting 2 sin x plus sin x sin 3x is equal to C2 C3 sin nx. Now apply sin c plus sin d, because in right hand side only sin x is here. So 2 sin c plus d by 2 into cos c minus d by 2. So we can see that 4 sin 2x into cos x is equal to c2 c3 sin x. After comparison, you can see c2 c3 is equal to 4 cos x, and sin nx is equal to sin 2x. So c2 c3 is equal to 4 cos x and n is equal to 2, and write all these value in your equation 4. So your final solution is this one. So this is your also 15 marks question, or can be 7.5 marks question. So just prepare wave equation, because in wave equation I have completed all the topics in this related to in this topic, wave equation. So uh, prepare your all topics, and the Alembert solution is very important. So prepare all topics. Thank you.